Dude! I think I know something that can go faster than light.
Go on.
What if I get a stick that's 1,000,000 miles long, maybe even touches the moon, and then I rotate the stick really fast? Wouldn't the tip of the stick move faster than the speed of light?
If you rotate the stick really fast, the energy would take time to travel throughout the object. Motion through objects propagates at the speed of sound.
Hear me out. Bro, let's get a satellite in space. Let's attach poles to the sides that extend slowly and have it spin really fast. Eventually, the tips of the poles will go faster than the speed of light.
Ignoring the fact that extending the pole would slow the box down due to the conservation of angular momentum and the small issue that this contraption would demand an infinite amount of energy to operate, it still wouldn't work. You're essentially trying to violate the fundamental limit set by relativity. Nothing in the universe can exceed the speed of light.
Okay. How about...
Jay, listen. If you find an object moving at the speed of light and you push it, it won't move any faster.
Even if I put huge rockets on it?
It won't work. Instead of getting faster, it will just become heavier.
That doesn't even make sense. You just made up a bunch of rules. How could you possibly know that?
Fine, I'll show you. Our story actually starts back in 1871, when Maxwell wrote down his equations describing electromagnetic fields. At the time, electricity and magnetism were thought of as two completely separate things, different rules, different boxes. What Maxwell did rather elegantly, I might add, was show that they're really just two sides of the same coin. An electric field in one frame of reference can show up as a magnetic field in another. Same physics, different perspective. And here's where it gets interesting. His equations didn't just unify electricity and magnetism. They also hinted at something deeper. They implied that light speed didn't depend on anything. Roughly 4 decades later, Lorentz in 1905 discovered his Lorentz transformation. He was able to explain away all the experimental results in his equations. But his equations implied that the speed of light is invariant to all observers.
Huh? What does invariant mean?
Alright, think of it this way. If you're in a car and you toss a ball forward, the ball's speed stacks on top of the car's speed. Pretty intuitive, right? But light isn't like that. Invariance means that light moves at the exact same speed. If you're standing still, if you're in a car, or even if you're moving at the speed of light.
Because of a random equation, you guys just started making up rules? Sometimes the math can give you a nonsensical answer. Sometimes the math says the rocket will hit the target -5 minutes ago, as in before I even fired it. Sometimes the math is absurd.
I was getting to the experiments, if you could just have some patience. Okay, let's start with the experiments. In the late 1800s, scientists ran a series of experiments trying to find anything that moved faster than light, and every one of them failed. The most famous was the Michelson-Morley experiment of 1887.
Oh, what was it?
They took a light source and sent its beam through a half-transparent mirror. Half the light went straight, the other half bounced at a right angle. Both beams traveled equal distances, reflected back, and recombined on the screen. The Earth moves 107,000 kilometers an hour around the Sun. This means the entire experimental setup is also moving at 107,000 kilometers an hour in some direction. According to classical mechanics, this would mean that the reflected light will appear faster than the perpendicular light. This should result in an interference pattern. This would mean that the light gets returned at slightly different times. This should be measurable on a detector. But every time they ran it, no matter the season or direction, the interference pattern never changed. The speed of light was exactly the same. That result was a pivotal turning point for physics. Modern versions of the Michelson-Morley experiment use what's called an optical resonator, two mirrors that trap light between them so precisely it forms a standing wave.
Whoa, it freezes light.
By comparing two resonators set at right angles, scientists can tell if light moves slightly faster in one direction than another. The entire setup is slowly rotated to test every orientation. Even after billions of attempts, the speed of light stays perfectly constant, matching Einstein's predictions. The speed of light was measured by many other experiments leading to the same conclusion.
What were they?
Fizeau measured the speed of light in moving water versus still water. The speed was the exact same. Up to this point, classical physics could still argue its way out. This experiment is where that illusion finally collapsed.
What was it?
The Earth orbits the Sun. When it's closer to the sun, the Earth is moving faster than when it's farther away. This means that the Earth's speed is changing throughout the year. In 1932, Kennedy and Thorndike built a version with one long arm and one short arm. They didn't rotate it. Instead, they waited as the Earth moved around the sun, changing its velocity through space. If the speed of light varied with the speed of the Earth, then there should be an interference pattern that shows up. But months passed and nothing shifted. That means light's speed stays constant even when our velocities changes. Exactly what Einstein's relativity predicts.
Okay, fine. Speed of light is constant. But what did Einstein even do?
The experiments of 1887 had baffled many scientists. Lorentz created an equation that could explain the null result of all the experiments. His equations assumed the speed of light is invariant, meaning it's the same for all observers. This was a big leap forward into understanding the physics. Lorentz didn't believe in the physical interpretations of his equations.
But bro, it's his own equations.
A few years later, Einstein extended the work of Lorentz. He was the first person to actually believe that the Lorentz transformation describes physical reality. He postulated that the following properties must exist: time dilation, length contraction, simultaneous events are not universal, and that space and time are fundamentally linked.
That sounds like a lot of copium. Like, why would anyone believe him?
Oh, they didn't. Like, get this. The science elites, total snobs. They were like, who's this random guy trying to drag Newton? Picture that one overachiever in class who's actually right, but everyone just thinks he's being cocky. That was Einstein.
Wait, so the science people hated him?
Pretty much. He sends out his theories and everyone's like, aw, cute, go get a real job. Brutal, right? But instead of losing it, he just keeps working, keeps publishing. Totally calm, like the unbothered king he was. And then people started whispering, wait, that patent clerk guy might actually be onto something.
Hold up, he was a patent clerk? Like not even a scientist?
Yeah, he was working a desk job, stamping forms all day, and meanwhile secretly rewriting the universe on his lunch breaks. Picture it, messy here, papers everywhere, but kind of adorable.
That's insane! Dude's doing cosmic math between coffee breaks.
Right? And then this big shot scientist, Max Planck, slides into his metaphorical DMs like, I don't totally get it, but you're kind of brilliant. And boom, first collab secured.
Bro got noticed.
Yep. Meanwhile, Einstein's broke, got kids, everyone's roasting him online, 1900 style. But he just shrugs and goes, if I'm wrong, one experiment will prove it. If I'm right, 10,000 haters won't change that. Like, total mic drop.
No way he said that. That's savage.
Oh, totally. And then 1919 hits. Someone finally tests his theory during a solar eclipse. And what do you know? It works. Newspapers lose their minds. Overnight, he goes from random clerk to global science elite. Paparazzi interviews, everyone's obsessed with his wild hair and dreamy, absent-minded look. Literal glow-up of the century.
So he actually becomes like famous?
Yup, and get this, he doesn't even brag. He's just like, wow, didn't think the press would get me better than my colleagues. Like, hello, humble icon.
Okay, not gonna lie, that's kinda badass. Dude turned being a nerd into a lifestyle.
Exactly. Einstein basically invented effortless genius chick.
I'm still a bit confused. What type of experiments were they running that was proving his wild theories?
So, there are these particles called muons. They're created high in the atmosphere when extremely energetic space particles collide with the air. Muons normally decay after only 2 millionths of a second. By classical physics, they shouldn't make it anywhere near the ground. But Einstein's equations predict that moving clocks tick slower. For a muon traveling close to the speed of light, time slows down in our reference frame, letting it live much longer. When scientists set up detectors on mountaintops and deep underground, they still found plenty of muons arriving. That was powerful proof that time dilation is real and that Einstein's relativity works.
How did Einstein know all of this before the experiments?
Imagine you have a light clock. You have 2 mirrors and a photon of light bouncing back and forth. Every time the photon hits the mirror, it ticks once. Now imagine this clock is moving. There's more distance the light has to travel. Since light speed is constant and each tick occurs slower, moving objects experience time slower. This is called time dilation.
But that's totally cap, unless we can practically measure time dilation.
We actually can. In 1938, Ira Stilwell proved time dilation. Ibis and Stillwell did an experiment and observed that if an object is moving close to light speed, then that light's frequency should slow down. When atoms are moving at high speeds, the light they emit is observed at a slightly different frequency.
Oh, I get it. It's like if I'm watching a YouTube video at 2x the speed, so I'm seeing it happen faster, but the characters experience it at the same speed.
I guess, yeah.
I have another example. Planes moving eastwards at full speed experience time moving 60 nanoseconds slower.
Okay, I can get on board with time dilation. I completely understand it now. In conclusion, Lorentz equations imply that nothing could go faster than light. We made some experiments where things should have moved faster than light, but they didn't. Einstein then said if nothing can go faster than light, then all these things should happen. We measured those things, proving that nothing can go faster than light. And we live in a simulation.
Wait. Where did you get that from?
It makes perfect sense. When I'm gaming and I'm moving too fast, my computer can't handle it, so I start rendering slower, which is basically like experienced time dilation. But my opponent isn't moving fast, so his computer can render everything at 60 frames per second, so he doesn't experience time dilation. So this proves that we live in a simulation.
See, I told you. Welcome aboard, Brother Jay. Come, let's hunt for the secret simulation society.
I don't get paid enough for this.